Consider the Boolean expression for an OR gate as shown here. Now that would involve me putting A and B through a 2-input OR gate, and when I've done this I look at the output of the OR gate and I can see that that in fact is A or B, as you would expect. Now I'm going to take this output as the input to a NOT gate, which will give me A or B knotted, as you can see there. Now if I take that now into another NOT gate, I will have it knotted twice, as we can see here. Let's consider the following combinations. A 0 and a 0 to the OR gate will give me a 0 at the output of the OR gate. This will act as an input to the NOT gate to give me a 1 at the output of the NOT gate, which will then be converted to a 0. Now if I input a 0 and a 1, I'll get a 1 at the output to the OR gate, which will go through the NOT gate to become a 0, which will then go through the next NOT gate to be turned back to a 1. If I now choose a 1 and a 0, what will happen here, I'll have another 1 at the output of the OR gate, which will get converted to a 0 by the NOT and then converted back to a 1. And finally, if I have two 1s at the input, what will happen there, I'll have a 1 at the output, then to a 0, and then back to a 1, as we've seen there. Now we should be able to note that the output here at the A or B part of the combinational logic circuit is exactly the same as the output shown here at the A or B double knotted. So in other words, it is quite clear for the input combinations given that these two outputs are identical. Consequently, we can say that this Boolean expression here must be the same as this one here in terms of its logic functionality, which means we can come up here and actually say that this is the same as A or B double knotted, which stands to common sense really, because if you take an expression and knot it, you turn it to its opposite, and if you knot it again, you bring it back to what it was right at the very beginning. And here the very beginning is in fact at this point here. We knotted it and then we knotted it again to give us this expression, but we've seen that the outputs are in fact exactly the same. Now this is a very useful feature when we wish to introduce the notion of universal gates, which means that we can build any combinational logic circuit using just one type of gate. And in this video I'm going to show you how we do that using Nand only. I've shown here the truth table for a Nand gate, which is this one here, and I've shown the logic symbol for a Nand gate. And what I'm going to do, I can see I've got two inputs here, but I'm going to take a tap of this one here and I'm going to join it to there. So this means that this particular gate can only be supplied with an input at this point here, and that input will then come along here and down here to this point. So whatever I place here will appear at this input here and will also appear at this input. Let's put a 0 at this point. Now that means that a 0 will be coming down here to this point. It also means that a 0 will appear here. Now when I do that, if I have a look at what I've got at the inputs here, I've got them both as a 0, which is this combination here. And when they're both a 0, I have at the output a 1. So that gives me a 1 at the output there. If I now put a 1 at the input here, then that 1 will in fact come down here to be a 1 here, and it'll obviously also come down here to be a 1 there. Now if I have a look at that condition, which is this one here, I can see that the output will be in fact a 0, so I'll have a 0 here. Now if you look very carefully, what we've got here is when the input was a 0, the output was a 1, and when the input was a 1, the output was a 0. We cannot have these conditions shown here that I'm highlighting in black here, look. Those conditions are not possible because we can only have an input here at this point, which gets split up to go to this input and this input here. So the combinations here are not possible when we join the inputs up, as you can see. But what we can see is when the input was a 0, we got a 1 at the output, and when the input is a 1, we got a 0 at the output. Now that, in fact, is the equivalent of a NOT gate. So in fact, what we can say here is if we join the inputs up of an NAND gate, we get the logic equivalent of a NOT gate. Now this is what enables us to build any combinational logic circuit out of just NAND gates. Let's consider the Boolean expression f is A or B. We can see that's for an OR gate. So we'll take that and we're going to double knot it so it doesn't affect its functionality. Now the next thing we're going to do is to use the bottom one, use De Morgan's theorem. So I can change the A to not A, I can change the OR to an and the B to not B. And then I can still maintain the not across the top. And what we've ended up with here is something referred to as a NAND expression, because there's only a NAND expression in there. There's no ORs, for example. So if I now take the A and I pass that through a NAND gate with its inputs coupled, I will get at the output a not A. If I take the B through a NAND gate with its inputs coupled, then what I will get a not B. Now I can take these to the input of a 2-input NAND gate, and what I will have at the output here are the inputs not A ANDed with not B, all knotted. Now we should be able to see that this expression here is in fact the same as this expression up here, which we showed was in fact the same as A or B, which is shown here. Consequently, although it doesn't look like, this circuit in fact performs the same logic functionality as a 2-input OR gate. This shows that we can build circuits using NAND only gates. Now the thing is, why would you want to do this? What's the purpose of this? Well, in truth, the answer to that is for another video. But very briefly, it simplifies the fabrication process when developing logic circuits, i.e. it's easier to fabricate the silicon if the patterns of the gates are all the same. And this happens when you have NAND only gate circuits. The next video in the series will show other examples of building combinational logic circuits using only NAND gates.